You're on mute or no?
Okay, it's Sunday morning, 11 o'clock, which means it's time for yet another Chai and Why. And this week again, we are going to be live from the lab, from the Molecular Dynamics and Control Lab, which the PI is Vaibhav Prabhudesai. And Vaibhav and his students are going to take us on a journey of how electrons interact with molecules. Is that true, Vaibhav?
Yeah, that's what more or less.
And maybe one can understand how electrons interact with molecules and use these things to control chemical reactions.
Yes, yes. That's
okay,
what we will see.
So that's what we're going to see today. Now, remember that we can't see you. So please do type in your questions, comments, etc. on the chat box if you're on Zoom, or Q&A if you're on Zoom, or the chat in YouTube or Facebook. And we will try and take those questions either during the session or at the end. Okay. So with that, let's go inside, meet your lab. This looks kind of wow, danger. Okay, let's be careful.
Yeah.
All right. Let's go. Please go.
Yeah. So ever since the discovery of electrons by J.J. Thomson, people have used electrons to explore and figure out the structure of matter, the structure of atoms, the structure of molecules, and and all these experiments actually used electron scattering from various objects to understand the internal structures as well as properties of the molecules, atoms, and all other such entities. What we do in our lab is use exactly the same method, that is the scattering of electrons from molecules, and try to understand how these electrons interact with molecules. And then we would like to explore, can we use this to control chemical reaction? Now, in order to understand the controlling chemical reaction, first we should understand what is chemical reaction. And before understanding chemical reaction, we should understand what is molecule and molecular bonds. So, Arnav, are you aware of molecules and molecular bonds?
Yeah, I think we remember something in school.
Yes.
Atoms come together and form molecules, and they either donate their electrons or receive their electrons, or if they are friends, they share their electrons with each other.
So as you can see, at the core of this bond formation or breaking is electron. So what are molecular bonds? They are basically nothing but shared or given or taken electrons. And what are chemical reaction is basically breaking and making of such bonds, and breaking a chemical or making a new chemical or molecule. And what we are trying to do is we are trying to use these electrons, putting them from outside, not from within the atom or molecule, but try to influence the molecule to form new bonds and break old bonds. And that's how we would like to see whether we can use this age-old technique of exploring molecules using low energy electrons with trying to see whether we can use this to control chemical reaction. So that's the major theme of this lab and the work that we.
All right, let's go. Yeah. Let's meet the heroes who do the work.
Yeah, absolutely. I mean, the students are the heroes, and they are the ones who actually perform the experiment for us. So we have
hi. So hi, who do we have here?
So that's Subhi and Akshay.
So we have Akshay Kumar. This is a real Akshay Kumar who works with molecules, and he's the hero of electrons and molecules. And Surbhi. So Akshay and Surbhi, let's go. देखते हैं लैब में क्या है.
So hello everyone. So as Vaibhav said, we work with low energy electrons. So low means what? Low means low.
एक मिनट अक्षय, पहले तो let's understand कि आप यहाँ पे करते क्या है, आपके ये एक्सपेरिमेंट कहाँ है आपका, ये इधर एक्सपेरिमेंट. ओके, So this is your experiment.
Yeah.
Okay. This is your experimental setup.
yeah.
And the experimental setup mein, what do you do?
So we do the electron and molecule interaction. So
You have electrons interacting with molecules.
yeah.
Okay,
So we
very
should
good.
have electron and we should have molecule to do the interaction. So for that we have electron gun, and for molecule we pass some gas. Here you can show the cylinder of various gases. Right now we have D2 SD and D2 and
Okay, okay. Let's go slow. Let's go slow. People will get confused. So you have electrons that are going to interact with gases.
yeah.
Okay. So in this chamber, electrons are going to interact with the gases.
Yeah.
Okay. So you need for that you need gases somewhere.
Yeah.
So gases. Oh, these are the gas cylinders. Which have your gases. Okay. इसमें क्या है?
इसमें hydrogen.
This is hydrogen. Okay. Very nice. But you have some small cylinders.
Yeah.
What are these?
These are SD.
HD. Okay, okay. That your D, the deuterium, the
Deuterium
isotope of hydrogen.
Heavy water,
the heavy water wala isotope. Yes, yes. So this is not H. Oh, this is H2, and this is
HD.
1H and 1D.
1D.
And that small
That
one
one D2.
is it's D2. Both of them are D.
Yeah. We want to see the isotope injection. That's why we have.
Okay, so these isotopes is also something that you study.
Yeah.
Okay, very good, very good. Okay, so we let's see what's happening. Why don't you बताओ क्या चल रहा है?
So we have we pass the gas through this path, and gas enters in this chamber, and it interacts with electron, and it forms ions, and then we guide that ion and see that ions on detector. So for that we can see the animation in here.
Okay. Let me try and understand. So, but the electrons कैसे बनाते हो?
Electron, we have some filament for which we can do the emission. So we can show you the actual filament of electron gun.
There's an electron gun.
Yeah, we have electron gun that emits the electron
Like you shoot electrons
yeah,
from
we
a gun.
shoot the electron molecule.
gun कहाँ पे है यहाँ पे?
गन थोड़ी दिखाएगी
कहाँ पे?
इधर तो अभी यहाँ पे लगी हुई है, पर हमारे स्पेयर में रखी हुई है ये इलेक्ट्रॉन गन.
So ये खोल नहीं सकते.
ये खोल नहीं
have
सकते,
another gun
vacuum
you
में
can see.
yeah.
So let's see an electron gun. I don't think I've ever seen an electron gun. So Surabhi, are you going to show us an electron gun? Okay, come.
So to make these electron and molecule interactions happen, we produce electrons of some like we can vary the energy of the electrons, and we want to study what is the effect of varying the energy of the electrons and how does it change the interaction that is happening. So for that we need electrons which are of different energies. And how do we produce these electrons? Well, you can okay, so this is something that is inside that chamber which Akshay just told you about, and here we can see I'll dismantle these electron gun for you, and I'll show you part by part. So this is a filament. So basically it's a very thin tungsten filament that we pass current across. So using a current source like 2 amperes of current, and then this leads to the production of a lot of electrons which are via thermionic emission. And now all these electrons, we give them, accelerate them by the energy that we want to accelerate them with, and that's how we get electrons of different energies, and we can control this energies in some EVs. And we here in this lab work with low energy electrons. Low energy for us is
what is low energy and what is EV and all this? I mean, I thought energy was, measured in
Joules.
calories or joules or something like that. Joules, right?
Yeah,
SI
yeah.
unit is joules and previously it was calories. What is EV?
So EV is a very fundamental unit of energy that we use for these small particles like electrons and molecules or something.
What is EV?
EV is
Electron volt.
So electrons accelerated by some voltage that we put across some electrodes, and you can create these electrons if you had the right assembly and all. You can even accelerate electron using these batteries, where this is 1.5 volts. So if you could accelerate an electron using this battery, you'd get an electron of 1.5 eV. So,
And what is your low EV energy range?
so we work with electrons up to this 9 volt battery can accelerate the electron up to can give the electron a 9 eV energy, and this is typically the energy range that we work with, 9 eV, 10 eV. So this is low energy electrons for us.
And why don't you want to use high energy electrons?
Well, higher energy electrons would lead to some other interesting things, like ionization of the molecules or something that we interacted with. But we here want to study the negative ion formation. So these electrons, they're low energy, they go and they interact with the molecule and they form a negative ion complex.
Okay, now I understand. So if you came in with very high energy electrons, the electrons have so much energy, it would strip other electrons from that atom.
Exactly.
We don't want to have that. You want to make a negative ion. So you want an electron to attach onto the ion.
Exactly.
So you send it with like low energy.
Yeah.
Okay. Now I remember. Yes. So I think you need 13.6 or something like that, right? To remove
an electron from
a
hydrogen
atom.
Yeah.
Of course, you work with molecules here, might be different. So that's why you're sort of less around 10 or so that you won't strip them off. You try and attach them.
Yeah.
That's what we're going to do.
Yeah.
Okay. So
Akshay is going to tell you more about.
I will talk about the chamber, about how that we work in our chamber. So let's see the animation video.
let's go and see this.
So I should, it will be on PPT also.
Okay, so now Akshay is going to actually show us what happens in this chamber, and for that he has an animation. And in the animation, what you see is this
is our chamber.
So from the left, can we just redo that? Just go back and come back again. Yeah. So what you will see is from the left, the gas molecules are coming in. The arrow that came from the top was the electrons, and the red things that were produced, those were the ions. Those were the ions that were produced, and they went and hit a screen on which there is a camera. Let's do this one more time. Just go start again so that we can. Can you just go to the first slide and come back to this? Yeah, and come back. Okay. So there come the gas molecules. There come the electrons, and the red things were the ions which went, and the things broke up. They formed some ions and they hit the screen. There's a camera on the screen, and they are detected over there. And let's see where it is over here. Let's switch back to the video now. So Akshay, so this is where the gas molecules come in, right?
Yeah,
so this is the gas molecules are going here.
This is electron.
The electron gun is on the top, so the electrons are coming down from there. And at the back side, hopefully there is your. Okay, here is the screen, and this is the camera. This is the CCD camera. So that's what the animation showed us. Okay, but इसमें दिखता क्या है? I mean, what happens? What do you see?
After
So you just.
So here, after the electron hits the MCB screen, we have some like MCB work like that. So when
that's the detector.
Yeah, detector. Micro channel plate detector. So we have several channels of micrometer. That's why name micro channel plate detector. So when an electron hits the detector, it generates a cascade of electrons. It's generally a particle amplifier.
Okay, so it like amplifies the number of count. Okay.
And this output electron then hit on phosphorus screen, and it has some photoactive material. And when particle hit on phosphorus screen, it generates glow. And that glow we can see by camera.
So you capture the glow by the camera.
Yeah.
And what happens when I look at, so you send electrons of different energies?
Yeah, we have different energies, like this low energy phenomena is resonance phenomena.
Okay. Yeah.
Like you have heard in school, like Bohr and 1 and equal to 2 level. So we have discrete energy level here also. So at particular energy we have maximum count. That's why we have.
So this is your energy.
Yeah.
So you're going from lower energy to higher energy. and you're seeing these things.
compounds. Yeah.
You want to just show the slide? It's probably clearer for this.
Yeah, we have
Yeah. Skip to the next one. Yeah. Okay. So on the slide, you see that there are some energies at which there is a much larger signal, and that is because at those energies the electron is getting absorbed. So there are multiple things. There is one small one, then a bigger one, then a very sharp one. So there are different energies at which the electron gets absorbed.
Yeah, it got absorbed and it will decay to H2 absorbed electron and it decay to H and H minus. And that H minus we detect on our first screen.
Okay, so you have hydrogen H2. So H2, when you add an electron to it, when the electron gets stuck, you have H2 minus. That breaks up into H minus and neutral H. And the H minus is the negative ion you're interested in. That is the ion which is going and hitting your screen. Okay. Okay, that's what you do over here. Okay. And you see some differences if you have these different gases over here?
Yeah, this peak that we are seeing is characteristics of different gases.
I
So
see. Okay.
if I have water, I have three different things. So it will depend on the gas. So once we find the resonance position, then we do the imaging and we can find the angular distribution. And for
Okay, so now then the next thing which you will do is you will fix your energy to one such position.
Yeah, yeah.
You fix your energy there, and then you want to see where are these ions coming around the thing. Are they going straight or are they going some angle? That's what you want to find.
how is the angular distribution?
The angular distribution. तो ठीक है, वो कैसे दिखता है?
वो के लिए कैमरे पे
यहाँ पे दिखेगा कि should we try the slide share only? Slide. Yeah.
So this is the
Okay, so this is the thing. What you're seeing on the screen now is this is of course a different example. This is not hydrogen. This is oxygen.
yeah
तो
oxygen.
यहाँ पे क्या हो रहा है?
O
Oxygen
negative
minus.
oxygen minus. Again electron interacts with O2 and produce O minus.
Okay, and there are three pictures. The
Yeah.
top one is at 8 electron volts. The middle one is at 6 electron volts.
And lower one is 5.
This is 5 electron volts. And depending on the energy,
We can control
you
the
can see where that.
angular distribution. How will it be?
So the top one, for example, there are 4 directions where it is maximum.
Yeah.
Whereas the bottom one, for example, it's only left and right or something where it is maximum. So depending on the energy, the direction in which these electrons go also changes.
Yeah,
so that is something which you study in the lab.
Yeah.
Okay. What
Like, so consider the case of hydrogen as.
So now this is hydrogen.
Yeah, hydrogen.
The next picture we are seeing is hydrogen, and this picture,
Like-
ये picture क्या है? ये जो यहाँ पे
ये
है.
पिक्चर ये से हाइड्रोजन का मॉलिक्यूल आप ये वाला मान लो.
So there is a hydrogen molecule. हाँ, 2 H
तो
है.
इसमें H सब कुछ सिमेट्रिक है, upward down it is symmetric. So we should expect electron distribution should also be symmetric. But in our experiment we didn't find that. So इसकी एक्सप्लेनेशन आती है क्वांटम इंटरफेरेंस से. तो क्वांटम इंटरफेरेंस की वजह से इसका मतलब फॉरवर्ड बैकवर्ड असिमेट्री आती है. ऊपर काउंट ज्यादा है, नीचे कम. यहाँ इलेक्ट्रॉन एनर्जी के साथ ये भी मतलब चेंज हो जाता है. ऊपर नीचे आएगा, नीचे कम आएगा. तो ये एक रियल कंट्रोल है कि हम इलेक्ट्रॉन एंगुलर डिस्ट्रीब्यूशन को कंट्रोल कर सकते हैं.
So here is the hydrogen versus the deuterium. So what changes is the
Electron.
angular distribution. So energy same है.
एनर्जी यहाँ पे 14.5 पे हाइड्रोजन और डी का कंपैरिजन है.
Okay, तो similar energies पे ऊपर हाइड्रोजन है, नीचे deuterium है. और deuterium में एक मतलब न्यूक्लियस थोड़ा अलग है, इसलिए वो इलेक्ट्रॉन्स के साथ भी इलेक्ट्रॉन अट्रैक्शन थोड़ा अलग होता है. तो बाहर का जब इलेक्ट्रॉन आता है उसका भी इंटरेक्शन थोड़ा अलग होता है. So you get different patterns for hydrogen and deuterium.
And as you can see from deuterium at 15 eV we have more counts at upward forward type and less count here. But when we scan the energy at 15 eV we have more count in backward direction as compared to forward. So we can change the angular distribution. So for example, for a certain reason, if we want that we want more count at this angle, not at backward angle, so we can tune that way to control our chemical reaction. So this is the control that we get via this interaction.
Okay. So basically, what we are trying to do is try and control which direction these ions are going to move. We can control that by changing the energy of the electron coming in. And this is what you will later on use to control.
Yeah, another control that we can get by fragment, which fragment, that should be will.
Okay. But I wanted to ask you something. ये जो experiment है ना, what are these? ये दो circles जैसे rings जैसे क्या है ये?
जैसे मैंने आपको बताया था ना, इलेक्ट्रॉन आता है, पर इलेक्ट्रॉन को हमें कॉलीमेट भी करना है, उसके लिए मतलब एक पर्टिकुलर डायरेक्शन में जाए, उसके लिए हम मैग्नेटिक फील्ड यूज करते हैं, तो ये हेल्महोल्ट्ज कॉइल है.
Helmholtz coil. What is a Helmholtz coil?
Helmholtz coils are used to generate like constant, like in 12, two coils in same direction of distance same as their radius. And
okay, this is something to generate a uniform magnetic field. Okay.
We can go to the big Helmholtz coil.
Yeah, we have.
Oh, you have a big Helmholtz coil. Okay, let's go to the big Helmholtz coil then.
So,
oh wow,
yeah,
that is a Helmholtz coil.
we just assembled this Helmholtz coil a few days ago. Helmholtz coil, as Arnav described,
Okay, we are here at the Helmholtz coil. So
Yeah.
a Helmholtz coil basically is
so
what is it? These are copper pipes. This is the coil, the pipe.
yeah, so
No,
you
these
know
are
what, how we produce magnetic field using Helmholtz coil.
I thought we produce magnetic field by sending a current
Exactly.
around the loop or something.
We send current in the, so there are two loops, one on top, one on bottom. Both of them send current in the same direction.
Wait, but these are not the coils.
These are not
the coils are actually in between here. The current carrying coils are inside here. This is the wire. These are the wires. The wires are going here. This looks like probably just some cooling water or something.
Exactly. So since the current
very
that
high.
we need is very high, we need something to cool this thing at all times. That's
Okay.
why we have these wire
So
connections.
these copper pipes are carrying cooling water.
Exactly.
The coils are actually, the wires are inside this, and a Helmholtz coil is such that the distance between the two is exactly the same as the radius, right? So the radius of this coil is the same as the separation between them. So when you have two coils like this, and the current is flowing in the same direction in both of them, then you get a very
Constant.
uniform magnetic field. And can you show us how the magnetic field looks like?
So
Yeah, you can see the magnetic field there.
Yeah. It's even there in one of the slides.
Okay, we can.
So we measured the magnetic field for this coil just a few days ago.
Okay, so the central region is very, very flat.
Yeah.
The central region of the coil is very flat. The magnetic field is almost constant in the center.
Yeah.
So you will put this Helmholtz coil around some equipment.
Yeah. So the electron gun that I talked about earlier,
Yeah.
where the electrons that come out, we don't want them going in all directions. We want to maximize the interaction between those electrons and the molecular beam that we are sending in. And to do that, we need these electrons to be collimated. And that is why we use this magnetic field, so that it keeps the electrons aligned, collimated, and in the maximizing the interaction with the molecules.
Okay, so otherwise the electrons could get lost somewhere. The magnetic field sort of helps trap them and keep them going in the same direction.
Yeah.
Okay. All right, great. So what do you do? Where is your experiment?
So you see it right over there. Next to Akshay.
Okay, and wow, let's go inside here. It's a little narrow, but I think I'm quite thin. I'll fit in. Okay.
That's my
Certainly
setup.
there's lots of electronics over here, and okay, there is. That's your setup.
Yeah.
Okay. Now, do you also have a source of gas and a source of electrons and a camera and things like this?
So I don't have a camera. I just have a detector at the end. But
Okay.
the rest of the things are very similar to what Akshay has.
So where is your gas? I don't see any big gas cylinders here. I mean,
So you'd have to walk again to these parts to find them. So gas over there.
oh, there. Yeah, I see it.
So here I don't. You see some gas cylinders, but
Yeah.
this is what is currently attached to my chamber right now, and this is a fluid inside a bulb.
Okay.
The fluid that I have right now is propylene oxide, And this,
Okay, so you're working on slightly larger molecules than what Akshay was doing, very simple hydrogen and deuterium.
yeah,
You're working on slightly bigger molecules. And right now you said you have a liquid,
yeah,
which is, what did you say it was?
propylene oxide.
Propylene oxide. Okay. All right. So you put a liquid inside your thing and you hit the liquid with electrons.
No, no.
No,
So what we study is
Too much sound
the
of vacuum
interaction of
sound.
gaseous molecules and the electrons. So this liquid that is connected right now will go inside it's connected to a vacuum chamber where it will become gaseous in form, and that's
Okay, so if you reduce the pressure, the liquid will actually boil at room temperature itself. You will get some of the molecules of the liquid coming up, and those molecules will go inside your chamber.
Yeah.
And you will hit it with electrons. So you also have electron gun.
Yes.
But you don't have a camera here.
I don't have a camera.
So how do you detect the things? What do you detect?
There's a lot of sound.
Oh, there's a lot of noise. Yeah, it's a noisy
Let's
lab.
come out of here.
Okay, let's come out. You can explain it probably in a, yeah. The thing is, there are lots of, where does the noise come from? Can you tell us where the noise comes from? We'll show them the pumps. We'll go outside and we'll show them the. So all these experiments need vacuum chambers, and these vacuum chambers have all kinds of pumps. Is this a pump?
Yeah, it's a servo.
This is a turbo pump, and then there are other pumps out here. These are oil pumps. So these are pumps which are running, and that's what's making the noise.
Yeah.
So can we go somewhere quieter to talk?
Yeah.
Okay. Oh yeah, this is so much quieter.
Yes, so remember when I said that my chamber is very similar to Akshay's chamber, but it is a little different. So it's different in the sense that I can study bigger molecules there because it gives me a better when I form these ions. So basically, I can separate out the ions with respect to their masses. So how do I do that? I do that in a mass spectrometer. So can you show them the slide of a mass spectrometer? I can explain. Yeah, so the outside of the chamber you guys saw, but this is what is there inside the chamber. So this is a schematic of something like we have inside our chamber. So it's a mass spectrometer where there is a.
You'll have to explain left and right because we can't see you. So you'll have to just explain what is happening in the left side, right side, etc. Okay. So yeah.
On the left side, you see there is a ionization area. So what we create are negative ions here. So there is a sample inlet, and then there is an electron gun going from top, which interacts and creates the negative ions that we wish to explore. And this negative ion, this breaks up into a neutral and another ion. And these ions, so now that these are ions, charged particles, we can accelerate them in electric fields. And that's how we accelerate them and take them to the detector. But I said that this chamber, we can separate out ions by their mass, and then we can study which ion was it that came to my detector. So how can we do that? So in this, if we give, suppose there are two people of like two things of different masses, one is heavy, one is light, but we give both of them same energy, then and we let them walk, or we fly them, then the thing that had larger mass will obviously be left behind, and the one of the lighter mass will come before. And this is how both of them will come in different time. And this is the technique that we use in mass spectrometers, where our ions, so where I can separate out ions with respect to their masses, and then we get some very interesting mass spectrums.
So basically, it's like this. It's like two runners. They come with the same energy.
Yeah.
And one of them is fat, one of them is really thin. The heavier guy is going to go slower. The energy is the same.
Yeah.
The lighter guy is going to go faster. So at your detector, the light ion comes first, the heavier ion comes later.
Yeah.
So depending on the time it took to come, you can figure out how heavy it was.
Exactly.
Okay. So you can see that this thing you work with bigger molecules. So the molecule gets the electrons, forms something, breaks up into different pieces. So those pieces are different sizes, so they have different weights, and hence they will move at different speeds. And then they come to your detector at different times. That's how you do this measurement.
Do you
So,
want to see?
Yeah. So can you show us how this?
Yeah, I'll show you one of the spectrums that we have.
Okay. All right.
Okay, so on the left over here, is the kind of spectrums that we see. So you will see here that we
So
basically
this plot on this side is mass. So the light guys are on the left, the heavy guys are on the right.
Yeah.
And you're seeing how many of them are coming.
Yeah, how many
Okay.
of them are coming and
what masses they are.
What masses they have, which
Okay.
on basis of which we can tell what ions they were, and then we can sort of speculate back what kind of process they came from.
And in this case, you started off with a molecule which is acetaldehyde.
Yeah.
I think they call it something else these days, ethanol or something. No, the UPSC guys keep changing all the names. Yeah, I think it's called ethanol. Anyway, so you had a CH3C double bond O and an H, but actually it broke up. So you're getting not one this molecule, but you're getting lots of smaller pieces.
Yeah.
So what are these pieces you see? You see some
CH3 minus.
there's a CH3 minus.
O minus.
There is an oxygen minus. Okay.
C2H minus.
C2H minus. So lots of different. So depending on how the molecule broke, you get these different pieces.
Yeah. And did you know that?
Does it just randomly break, or I mean, does it depend on what you do to it to make it break?
So what we have to vary here is the energy of the electron. And as we change the energy of the electron towards the right, you can see. So on the x-axis, you'll see some energies like 14.
Whatever, it's some energy.
Some energies.
Okay.
And then you'll see on the y-axis that there is counts. So
Correct.
I see maximum number of counts at some certain energy. So do you know this process is, you would have seen things like this is a resonant plot. So I am getting maximum ions at one particular energy, and varying based on the energy of the electron, I can break apart the molecule in different ways, obtain different ions, and
So you can actually control how you break the molecule.
Exactly.
Whether you want to break that oxygen wala bond or you want to break the hydrogen somewhere, you can actually control how in a molecule which bond to break.
Which bond to break.
By coming in with the electron the right energy.
Yeah.
Okay.
And so exactly, I'll show you another example of what we saw in our labs.
Okay.
So here I show you three molecules: acetyl acetone, acetone, and ethyl alcohol. So don't worry about the names and all. So here you'll see. So here, when we studied electron interaction to this molecule, acetyl acetone, we saw that H minus was coming at 8.5 eV. So 8.5 eV was the energy of the electron that caused H minus to form. And then this H minus from this molecule can come from, as you see, the red, the orange site. Okay, can you go back to the slides?
Okay, let's just go to the camera first. Yeah, you settle down. Yeah, so let's just while he gets that slide again, let's so you had different molecules and you are coming in with electrons of a different energy, and you find that, for example, for acetyl acetone, if you come with 8.5 eV energy, then some particular bond breaks.
Yeah. So how do we know which bond breaks? That's what we.
Do you want to go back to your slide?
Yeah, sure.
Okay. Okay, there we are. Okay, so
the source of this H minus over here can be this OH, the H attached with the O, and these H that are attached with the carbon atoms. And so we only see H minus, we don't know where it is coming from. So to know where it is coming from, we sort of compared it to the other molecules, and we were able to do this because there is something called a functional group site selectivity which exists for electron interaction with molecules. And we saw that in acetone, the middle molecule, where there are only one kind of H site available, like the CH bond, and from there the H is coming at H minus, we saw used to come at 8.4 eV. And from ethyl alcohol, which has the other kind of H atom, which is only attached to the oxygen, we saw that the ion came at 6.5 eV. So this sort of tells us that if this electron from acetylacetone is coming at 8.5 eV, then it must be coming from the CH site on comparison. Like when we compare it to other molecules, this tells us it must be coming from the CH site and not the OH site. So this way I know that my electron broke a specific bond, the CH bond. And this is how we can in principle break bonds selectively. But can we also make bonds selectively, things like this? So let's go to Vaibhav, and he will talk more about how we can use this selective bond breaking.
So let's get Vaibhav back. And
yeah, okay. Thanks
So-
for showing this whatever that we are doing. So so now let's come back to the main theme of what we are doing. So as Akshay and Surbhi has shown to all of you, that we use this electron scattering. We use this electron scattering to look at how these electrons interact with molecule and how does it result in the formation of negative ions, and how these negative ions break at different sites depending on what is the energy of the incoming electron. And we have seen that we have a control in which bond that can be broken. Now remember, that means we have done the half job of chemical reaction, because as I said in the beginning, what is a chemical reaction? It is basically a breaking a bond and a making of a bond. So I have already shown you that we can use these electrons as a tool to break a bond selectively. In fact, a very interesting story that goes behind this control of chemical reaction is that when the lasers were invented in 1960s and 70s, the first thing that people thought about is that since now I have a control on the light field and the photon wavelength, I can in principle break whichever bond I want by selectively putting in light of a specific wavelength. Now, something similar is what we are doing, but instead of photons, we are using electrons. And we are putting in these electrons in the molecule and making a negative ions. And these negative ions break and form fragments. Now, as you saw in the experiments, all the experiments that took place, they were in vacuum. And one electron was interacting with only one molecule. So if that happens, the chemical reaction will never take place, because for chemical reaction to happen, two molecules or atoms have to come together and form bonds. Now, as a result, what we should do is that we should carry on this process on a place where we have several molecules coming together. And that's what we have done in another experiment, which I will not show now, but just describe to you, that we take molecules in the condensed phase. So we have a surface over which we deposit molecules, and then we irradiate it with these electrons and try to see what kind of new bonds which are being formed. And that's where we have found that we can actually use this electron not only to break the bond, but also to form the bonds. And that is what is the theme that we are pursuing in this lab. Now, why are we doing this? And when we do this, what are the new things that we found out? So as you guys all aware of something called catalyst, where an entity that is added to the chemical reaction and that changes the rate of chemical reaction, but does not take part in the chemical reaction. What we have shown is that by breaking and making bonds, the electrons can also act like catalysts. So the free electrons that are coming out of these filaments, they can also act like a catalyst. Now, this is a totally new concept, which was not understood till a decade ago, but now we have shown it experimentally that this is what indeed happens when electrons interact with a lot of molecules in the condensed phase. And now we are trying to use this to control and see whether we can form new molecules or not. So for example, we have done an experiment where we have taken carbon monoxide and oxygen, and we have formed carbon dioxide from it by putting electrons. We have taken methane and oxygen mixture and irradiated with electron, and we have formed alcohol from this. So these are the kind of reactions that we are looking into, and we are trying to see whether we can control these reactions by this negative ion route. Now, you might be wondering that, okay, so we are doing some things in some isolated molecules and interacting with them with electron. Why are we doing this? What is so special about it? So these kind of interactions, you will be surprised to know, actually do happen in astronomical objects, where cosmic rays interact with the gas and dust particles, create electrons which are lower energy, and these lower energy electrons can interact with molecules and atoms which are deposited on dust particles and generate new molecules. So that's astrochemistry for you. Then when the cancer therapy happens, where the radiation dosage is given to tumors, and these radiation dosages actually create a lot of low energy electrons of the order of 0 to 10 eV. And these low energy electrons, they go and attach to the DNA molecule of the cell. And when they attach, just like what Akshay and Surbhi showed you, that when the electron has attached to H2 or acetyl, acetone, or ethanol molecule, the molecule became a negative ion and it just broke. Similarly, the DNA, when it attaches electron, low energy electron, that also can break. And when it breaks, if it breaks at, so the DNA is a double strand, right? It's a helix of double strand. If only one strand breaks, then it will not kill the cell. But if the two strands break, then it can kill the cell. So these are the negative ions which actually are responsible for killing or rather curing the tumor by killing these cancerous cells. And these kind of studies are also important to understand how these things happen, because once you understand how these radiation cure tumor, you can actually improve upon it, improve upon the technology, improve upon the dosages, and also decide how much dosage one should give in order to make the optimum use of the radiation without damaging the healthy cells. So that's another place where these kind of studies are interesting and are important. The third place is basically atmospheric chemistry. So again, in our atmosphere, you have all sorts of radiations like UV light and cosmic rays and all other kinds of particles which are interacting with gases like ozone and oxygen and nitrogen, and they cause a lot of chemical reactions. But most of these charged particles or a UV light, when it interacts with atoms and molecules in atmosphere, it actually generates lots of low energy electrons which interact with molecules and can break those and create chemistry in atmosphere. So all these reactions that we are studying over here and all these reactions that we are trying to control over here are relevant in astrochemistry, they are relevant in atmospheric chemistry, they are relevant in radiation biology, they are also relevant in plasma. Okay, so for example, plasma is a soup of positive ions and electrons, and there you have a lot of electrons, free electrons with very low energy, and they can determine the composition of plasma, which can be used in industries to have a specific outcomes in the electronic chip making, or on writing micron or nano-sized structures on the surfaces. So even there, the low energy electrons interactions with molecules are very, very important. And how do these low energy electrons interact, and what exactly kind of chemical reactions they form, and whether we can control those or not is something that we do in our lab. So that's the
awesome.
physics of chemical reactions.
It was really nice to see that this basic research is actually so important to understand what's happening in the atmosphere, what's happening in outer space, and what's happening even when they do chemotherapy. But you said lasers were used to control reaction. I thought we saw some lasers in your lab and all these danger laser signs also.
Yeah.
So are there some interesting lasers in your lab?
Yeah, sure. So we will show you.
All right, let's go back and let's look at some cool lasers. And are you also trying to use lasers in your experiments?
Yeah. So we will.
Yeah. So this is one of the lasers that we have, which is aligned with my chamber right now.
Which is the laser? I mean, people are used to seeing laser pointers, small little things, and all. This is a massive laser, right? I mean, here is Surbhi for size, and that is the laser. This whole thing is a laser. This big box, this big black box is the laser. What type of a laser is this?
This is called an excimer laser.
An excimer laser, okay.
Yeah.
And it's got a lot of, I see a gas tank here. I see another gas cylinder here. I see another gas cylinder here. And what are these? Let's can we...
This is krypton.
This says it's krypton. Okay, that's interesting. I think the first time I'm seeing a krypton cylinder. And what do we have down here?
This is fluorine. 5% fluorine in krypton.
This is fluorine.
Yeah.
Wow, isn't that supposed to be really highly reactive and yeah.
Yeah.
So this is a gas laser effectively.
Yeah.
Yeah. So, and where does the light come from?
And so this is a UV laser.
Oh, so you can't see the light.
You can't see the light.
Okay, so the light is coming out from somewhere here.
Somewhere over here, the light comes out.
Okay, the light comes out of this, probably out of this aperture here, this hole here, and then it goes inside your chamber somehow.
Yeah. So
so
this would give me a 248 nanometer color, which is UV. And what we plan to do with it is so right now you studied saw negative ion formation happens with electron attachment. What we want to do is to dissociate these molecules with the laser, with the 248 nanometer laser, break apart the molecule, particularly acetylacetone is what we are interested in right now, and we'll see OH radical which will be formed, and we want to study how electron attachment happens to OH radical. So this OH is something that is there present in our, as Vaibhav talked to you about astrochemistry, the importance of studying these reactions in astrochemistry. There, a lot of OH radicals are present, which act as the main reducing agent for a lot of pollutants. And and there are a lot of free low energy electrons hanging out there as well. So we want to know how this interaction of electron happens with OH radicals, and that's what we plan to study. But you can also look at the cool laser that we have. We want to talk about how this.
how does the laser work?
Yeah.
Oh, you want me to say?
Yeah.
Okay, why not? Why not? So, so basically, if you want any laser, okay, you need three things. You need some system where there are more people upstairs at a higher energy level than downstairs. So you need what is called population inversion. You need more people, higher energy level than lower energy level. And this is done by, somehow exciting a gas. So you have helium neon lasers and you have that laser. Every particular atom or molecule that you take has some energy levels, and based on that, it will emit a different sort of color of light. Only if you have now usually electrons and electrons and molecules or whatever, they're all lazy. Everybody wants to be at the lowest energy state possible. Okay, this is where the excimer helps you. The excimer is excited dimer, two molecules, krypton and fluorine. Now, normally you think these krypton, xenon, all these inert gases, they're supposed to be inert or noble gases. They don't react, but they actually do react with other very energetic atoms like fluorine. So krypton and fluorine will react. Now, the strange thing is, krypton and fluorine, when they come together in the lowest energy, that's unstable. That's absolutely unstable. But if you give it enough energy, which you do by putting a high, putting in between some high voltage, so you need high voltage, the excited state turns out to be stable. The lowest energy is not stable, but the excited state is stable. The higher energy is stable, which automatically means that you have much more people upstairs because that's stable. Imagine if the first floor was very nice, ground floor, nobody wants to live. You have more people in the first floor than the ground floor. This is how in krypton fluoride and xenon fluoride and other things, you can get this very important thing called population inversion that you need for a laser to work. So these are called excimers, excited dimers, but actually it's not a very easy molecule like the typical oxygen O2 dimer or something. So it's also actually called an exciplex sometimes, excited complex. You might hear this word as well. So I said one thing, you need more people upstairs and downstairs. You also need mirrors because the light that is there has to bounce around and you need lots of light before this lasing action actually happens. So there are mirrors you need. And of course, if the light is going to go out, you need to supply energy. This energy can be, it's usually electrical, via high voltage or something, or it could be different ways of supplying energy. But in this case, it's krypton and fluorine reacting to form krypton fluoride in an excited state, and that actually lasers. And by the way, this krypton fluoride laser, without this, you wouldn't have your mobile phones or any electronic or high-end computers and everything else, because the 248 nanometer light that it makes, the ultraviolet light, is what is used or has been used for the last say 15 years or so you write with light to make these circuits, and all that uses the krypton fluoride 248. This has been the workhorse of getting all these circuits made in industry. So it's actually a very, very important laser. It's big. We have some more lasers out here. These also look like lasers. There's also different kinds of lasers here. So these are also, you see, this is some laser here. This is a different laser. This is what kind of a laser is this? This is a YAG laser, right?
No, this is NDR.
Oh, this is a YAG laser. And that's a dye laser. So there are lots of different types of lasers, all so that we can get a particular color of light that we want for a reaction. Okay, I think it's again very noisy here, so we should probably go out and see if there are some questions people have.
But I have two interesting points that will again relate to what we do in the lab. Number one is, as Arnav said, the krypton fluoride laser, the krypton fluoride molecule is more stable in the excited state than in the ground state. And the way to excite it is actually by sparks. And the sparks are electrons. And these are the electrons which actually come, interact with molecules, excite them, and make them form the excited states of the krypton fluoride in this case. But in other cases like xenon fluoride or argon fluoride and so on and so forth. That's one part. The second point is that Arnav said that 248 nanometer light was used to write things on the chip, which have been used in your mobile phone and all other electronic devices. People are now trying to go in smaller and smaller sizes, and that's where the light is not going to be of any use. So in order to go to the smaller and smaller sizes, people are looking at charged particles being used to write these patterns.
Yeah, you can write with electrons.
Exactly, and that's what people are trying to do. People are trying to put in electron beams to get as small writings on the chips. But then, if you know how these electrons are going to interact with the surface and the substance over which you are going to write, you can actually control the effectiveness of these electrons on this writing process. And that's the plasma etching that I was talking about. And again, what we study in this lab forms the fundamental understanding of how these electrons can be used in this process. So I just wanted to bring
the moral of the story is understanding basic science is very important. Tomorrow you're not going to come up with a better way to make chips, but the understanding that we get is actually important in the process of technology that gets developed maybe years later. Yeah. Right? Okay, so let's look at if there are any questions on the thing. You can be here. I'll just quickly see if the chat there are something. Okay. There were some questions. Okay. All right. So there are some questions. What is EV again? Is electron volt. Could you please explain? Sahil wants to know what is electron volt and what is EV. EV is electron volt, and how is it? What is the relevance of this electron volt?
Okay. So, in the simplest way, I can explain what is electron volt is following. That you take any charge particle, and if it has a charge, say +1, and now if I accelerate this charge particle from one point to another point in such a way that the 2 points have a potential difference of 1 volt. So if this should be showed you that 1.5 volt battery. So if I now connect the 2 ends of the battery to 2 plates, and if I start a charge particle to start from one end and reach to the other end, when it reaches the other end, it has already gained an energy of 1.5 electron volt. So that's the simplest way one can understand that when a charge particle moves from one point to another point, the amount of energy that it gains because of the difference in potential of those 2 points, that's the electron volt of energy that the charge particle gains. So that's the simplest way of looking at it. And just to put it in a proper scaling, the hydrogen atom comprises of 1 proton and 1 electron, and the binding energy of this electron with the hydrogen atom is 13.6 electron volt. So what it means is that suppose if there are 2 stationary particles, the energy, the potential between the two is of the order of 13.6 volt. So that's what is the typical scale.
Okay, thanks. Vaibhav. There's another question from Abhinav Chaudhary, who asks, do the electrons displaying their own quantum mechanical nature, i.e. the states such as momentum and position, can induce coherence in other molecules? This is a question I don't know if it makes sense.
Yes, that is absolutely right. These electrons, so if you consider electron as a particle, then of course the electron comes, attaches, and then you form the negative ion, and that's all. But if the electron behaves like a wave, then this attaching electron can actually transfer several angular momenta, which can be part of this wave nature of the particle. And as a result, it can cause coherence. And that's what Akshay showed you, that for molecule like hydrogen, where there are 2 hydrogen atoms which are identical to each other, but I can still control whether the electron resides with the top hydrogen or the bottom hydrogen simply by playing with this coherence. So that's where the wave nature of electron plays a role, and the coherence plays a role. Yeah.
Okay. Okay. There's another question which I think you were explaining various things. You said this is also relevant to plasma. So how is this thing relevant to plasma as a question?
Yeah. So as I said, plasma is typically a soup of positive and negative, positive ions and electrons. And there, if you are going to cold plasmas where we are generating lots of electrons, then these electrons can interact with neutral molecules, and these neutral molecules will form negative ions and they will dissociate. But that will decide the chemistry of that plasma, the composition of that plasma, which effectively result into various reactions that might end up with with specific properties given to the plasma, and this can be used in semiconductor industry to actually transform the silicon surfaces or the microchip cut surfaces the way in which you want. So that's where these understandings play a role. In fact, the krypton fluoride laser that you talked about, inside when we are generating sparks by putting high voltages, we are actually putting in electron and we are generating plasma, and the chemistry of this krypton fluoride excited state being bound is actually controlled by the electron interaction with this plasma. So here is another example of how this is relevant to plasma.
Okay, there's another question from Kshitij. He asks, which ion detector was used in mass spectrometry for Surbhi-G's setup?
So the detector that we used was a channeltron. So that is also Akshay explained to you the working of an MCP. So on channeltron as well, the ion hits with some momentum, and a bunch of electrons are generated, and this electron bunch forms the current that we see as the signal for our ion detector.
So in other words, the detector that Akshay used is actually made of several such channeltrons, each of them of micron size. So that's why that is called microchannel plate. But each of these microchannel is actually a channeltron on its own, and the bigger version of that is what Surabhi uses in a setup. Yeah.
Okay, last chance. If there are people who have questions, please put them in, and we will try and answer them. Meanwhile, there is somebody who has anonymous has put in the lyrics of a song. He says, or she says, every move you make, every bond you break, I'll be watching you. I think that's what you guys have been doing. Okay,
Good.
So,
we also do watch every bond we make. And
right, right. So are there? I do not see any questions in the Q&A box or the chat. Divya, are there any questions on Facebook?
No, no
Comments?
question.
Anything to
No.
be?
No, on Facebook, nothing.
Okay, all right. Okay, so then let us before we end, of course, we need to thank Vaibhav, Surabhi, and Akshay for taking the time
Sorry,
to show
Arnav,
us these little intricate things that they do in the lab. Remember, October has 5 Sundays, and we will have a 5th Sunday Chai and Wai. Since the 5th Sunday Chai and Wai is always a Chai and Wai, which is typically a hands-on thing, we are trying to bring you a set of fun experiments you can join us and do at home. Okay, so that's going to be happening on 31st of October, Sunday 31st October, our 5th Sunday Chai and Wai, hands-on experiments for you to join us and try at home. Very simple stuff. Following that, the first Sunday of November, November 7th, that's our Diwali special. November 4th is Diwali, and always the Chai and Wai that's been closest to Diwali has been something to do with light. So we will have fun with light, still deciding. It is possible, no guarantees that depending on the government guidelines for theaters, etc., we may be able to have a physical session, but there will always be an online session. So it's definitely online. We are not sure as yet whether it might be also a physical session. We will let you know. Do follow us. Thank you for watching, and have a nice weekend. Thank you.